Hello students. Today let us discuss the exercise of the lesson transition and inner transition elements. Question number 1. Choose the most correct option. First question. Which one of the following is diamagnetic? The correct answer is option D, Sc3+, since there is no unpaired electrons. Second question. Most stable oxidation state of titanium is, the correct answer is option C, +4. The electronic configuration of titanium is Ar3d2 4s2. By losing the 4 electrons, 2 from 4s and 2 from 3d, it forms titanium +4 ion. So which is the most stable oxidation state. Third question. Components of nichrome alloy are nickel and chromium. The correct answer is option C. Fourth question. Most stable oxidation state of ruthenium is, answer is +4, option B. Fifth question. Stable oxidation state of chromium R. Answer is +2 and +3. Correct answer is option A. Sixth question. Electronic configuration of copper and Cu+1. Answer is, for copper, 3d10 4s0. And Cu+1, 1 electron is lost, so the electronic configuration is 3d9 4s0. Correct answer is option A. Seventh question. Which of the following has D0 S0 configuration? The correct answer is option D, all the above. We know the electronic configuration of scandium is D1S2. When it is forming Sc3+ ion, it will lose 1 electron from d orbital and 2 electron from s orbital. So the electronic configuration becomes D0S0. Titanium is having the electronic configuration D2S2. When it is forming Ti4+, it will lose the 4 electrons from d and s orbital. And vanadium is having the electronic configuration D3S2. When it is forming V+5 oxidation state, it will lose the 3 electrons from d orbital and 2 electrons from s orbital, and the electronic configuration become D0S0. So the correct answer is option D. All Sc3+, Ti4+, and V5+ have the electronic configuration D0S0. Eighth question. Magnetic moment of a metal complex is 5.9 Bohr magneton. The number of unpaired electrons in the complex is, the correct answer is option D, 5. That is, the formula to find out the magnetic moment is mu is equal to square root of n into n+2. If the number of unpaired electron is 5, square root of n into n+2 become square root of 35. Square root of 35 is 5.9 Bohr magneton. So the number of unpaired electron is 5. Ninth question. In which of the following series all the elements are radioactive in nature? Answer is B, actinides. In actinides, all the elements are radioactive in nature. 10th question. Which of the following sets of ions contain only paramagnetic ions? Paramagnetic ions contains unpaired electrons. So the correct answer is option D, Ce3+, Eu3+, Yb3+. They all contains unpaired electrons, hence they are paramagnetic. Ninth question. Which actinoid other than uranium occur in significant amount naturally? The answer is thorium. Correct answer is option A. Answer the following. First question. What are the stable oxidation state of plutonium, cerium, manganese, europium? Answer is, the stable oxidation state of plutonium is +4, cerium is +2, +3, +4, manganese is +2 to +7, and europium is +2 to +2, +3. Second question. Write the probable electronic configuration of chromium and copper. We know chromium and copper is having the exceptional electronic configuration due to the additional stability it is getting due to half-filled and completely filled state. So the probable or expected electronic configuration of chromium is Ar3d4 4s2. But the observed electronic configuration is Ar3 3d5 4s1. The probable and expected electronic configuration of copper is AIR 3d9 4s2. But the observed electronic configuration of copper is AIR 3d10 4s1. Third question. Why nobelium is the only actinoid with a +2 oxidation state? Answer. The electronic configuration of nobelium is Rn 5f14 6d0 7s2. After losing 2 electrons, nobelium forms NO2 plus ion, which is stable due to completely filled 5f orbitals. Such extra stability is due to completely filled orbital is not acquired by any other actinoid in their +2 oxidation state. Hence, nobelium is the only actinoid with a +2 oxidation state. Fourth question. What is meant by shielding of electrons in an atom? Answer. The decrease in the force of attraction exerted by the nucleus on valence electron due to the presence of electrons in the inner shells is called shielding effect. As a result of shielding effect, the effective nuclear charge experienced by the valence electron is less than the actual nuclear charge. Explain with the help of a balanced chemical equation why the solution of cerium-4 is acidic. Answer. According to Lewis acid theory, a species that can accept a pair of electrons is an acid, or acids are electron pair acceptors. The electronic configuration of cerium is Xe 4f1 5d1 6s2, and that of cerium in +4 oxidation state is Xe, that is after losing the 4 electrons, 2 from 6s, 1 from 5d and 1 from 4f, it takes the electronic configuration of xenon. Cerium-4 can accept lone pair of electrons from water molecules in its vacant orbitals to form the complex. That is Ce plus 4 plus NH2O gives CeH2O n times plus 4. Hence, solution of cerium-4 is acidic in nature. Next question. Atomic number of an element is 90. Is this element diamagnetic or paramagnetic? We know for diamagnetic substances contain paired electrons and paramagnetic substances contain unpaired electrons. The electronic configuration of the element with the atomic number 90 is Rn 5f0 6d2 7s2. Here you can see 2 unpaired electrons in the 6d orbital of the element. Hence it is paramagnetic. Next question. Explain the trends in atomic radii of d block elements. Answer. Atomic radii of the elements of transition series decreases gradually from left to right. We have seen lanthanide contraction. As we move across the transition series from left to right, the nuclear charge increases by 1 unit at a time. The last filled electron enters the penultimate n-1 d subshell. However, d orbitals in an atom are less penetrating or more diffuse, and therefore d electrons offer smaller screening effect. The result is that effective nuclear charge also increases as the atomic number increases along with the transition series. Hence, atomic radii gradually decreases across the transition series from left to right. Question D. Iron exhibit +2 and +3 oxidation state. Write their electronic configuration. Which will be more stable and why? Electronic configuration of Fe2 plus is 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. And electronic configuration of Fe3 plus is 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. Here you can see Fe3 plus is more stable than Fe2 plus. This is due to the presence of half-filled d orbital. Fe3 plus d orbital is half-filled state. So, Fe3 plus is more stable than Fe2 plus. Question E. Give the similarities and differences in the elements of 3D, 4D and 5D series. First, let us see the similarities in physical properties of the series. Number 1. All D block elements are lustrous and shining. Number 2. They are hard and have high density. Number 3. They have high melting point and boiling point. Number 4. they are good electrical and thermal conductors. Number 5, they have high tensile strength and malleability. Number 6, they can form alloys with the transition and non-transition elements. Number 7, many metals and their compounds are paramagnetic. Number 8, most of the metals are efficient catalysts. Now, similarities in chemical properties. Number 1, all D block elements are electropositive metals. Number 2, they exhibit variable valencies and form colored salts and complexes. Number 3, they are good reducing agents. Number 4, they form insoluble oxides and hydroxide. Number 5, iron, cobalt, copper, molybdenum and zinc are biologically important metals. Number 6, they catalyze biological reactions. Now let us see what is the differences of the different transition series. Although most properties exhibited by D block elements are similar, the elements of first row differs from the second and third rows in the stabilization of their higher oxidation state in their compounds. Question F. Explain trends in ionization enthalpies of D block elements. Answer. The ionization enthalpies of transition elements are intermediate between those of S block or P block elements. This suggests that transition elements are less electropositive than elements of group 1 and 2. As the atomic number increases across the transition series, the first ionization energy increases with some irregularities. Ionization enthalpies for a given element increases from the first ionization enthalpy IE1 to the third ionization enthalpy IE3. The atoms of elements of third transition series possess filled 4f orbitals. 4f orbital shows a poor shielding effect on account of their peculiar diffused shape. As a result, the valence electron experiences greater nuclear attraction. A greater amount of energy is required to ionize elements of third transition series. The ionization enthalpies of the elements of third transition series are therefore much higher than the first and second series. Question G. What is meant by diamagnetic and paramagnetic? Give one example of diamagnetic and paramagnetic transition metal and lanthanoid metal. Answer. The substances with all electrons paired are weakly repelled by magnetic field. Such substances are called diamagnetic substances. So, diamagnetic substance contain paired electrons. The substances with unpaired electrons are weakly attracted by magnetic field. Such substances are called paramagnetic substances. So, paramagnetic substances contain unpaired electrons. Example, diamagnetic transition metal, zinc, lanthanoid metal, terbium. Paramagnetic transition metal, titanium, lanthanoid metal, cerium. Question H. Why the ground state electronic configuration of gadolinium and lutetium are different than expected? Answer. Gadolinium and lutetium show different ground state electronic configurations because the 5d and 4f orbitals are near to the same energy, due to which the next electron goes in 5d orbital instead of 4f orbital. This retains the extra stability achieved when the 4f orbital is half filled and completely filled respectively. Thus, 5d orbital contains one electron in the case of gadolinium and lutetium. Question J. Cerium and terbium behaves as good oxidizing agents in the +4 oxidation state. Explain. Answer. Cerium and terbium shows +4 oxidation state. Their electronic configurations are cerium, Xc, 4f1, 5d1, 6s2. In +4 oxidation state, the electronic configuration is xenon configuration. Terbium, electronic configuration is Xc, 4f9, 6s2. In +4 state, the electronic configuration is Xc, 4f7. From this, it is clear that the electronic configuration of Ce at +4 state is favored by its noble gas configuration. But It can be easily converted into stable Ce3+ by the gain of an electron. Due to this reason, Ce+4 is a good oxidizing agent. Similarly, Tb+4 ion is stabilized due to a half-filled F subshell. It can be easily converted into stable Tb3+ by gain of an electron. Due to this reason, Tb4+ is a good oxidizing agent. Question K. Europium and ytterbium behaves as good reducing agents in the +2 oxidation state. Explain. Answer. Europium and ytterbium shows +2 oxidation state. Their electronic configurations are europium Xe4f7 6s2. In +2 oxidation state, it is Xe4f7 by the loss of 2 electrons from 6s orbital. Similarly, ytterbium, the electronic configuration is Xe4f14 6s2. In +2 state, electronic configuration is Xe4f14 by the loss of 2 electrons from 6s orbital. From this, it is clear that the electronic configuration of EU in +2 state is favored by its half-filled F subshell. Here you can see 4f7 electronic configuration. But it can be easily converted into stable EU3+ by the loss of an electron. Due to this reason, EU2+ is a good reducing agent. Similarly, terbium in the +2 oxidation state, ion is stabilized due to the completely filled F subshell, F14. It can be easily converted into Yb3+ by the loss of an electron. Due to this reason, Yb2+ is a good reducing agent. So students, we have discussed all the question answers according to the revised syllabus. Please read the textbook and study well. Thank you.